Hi. So in this lecture, we will learn about cross-validation. It's an important topic in the field of machine learning and AI. Cross-validation is perhaps the most important thing when you build a machine learning model, right? Building the model is not necessarily a very difficult job, but assessing its performance, ensuring that it's not overfit, it's ensuring that it really works in a new situation within a new data set is very, very important. And that's where cross-validation really helps a lot. And therefore we need to understand cross validation in detail and how to do it, but what are the do's and don'ts related to cross validation, and what are the important things to keep in mind while doing cross validation. So in this lecture we will learn about first what is cross validation, different types of cross validation, the packages available in Python and R, and what are the do's and don'ts related to cross validation that you need to be careful about. Okay. So what is cross validation, right? If you have ever built a machine learning model, you know that when you get a data set, right, you split that into two data set, right? One is the training data, the other one is the test data. You build the model in training data and you test the performance of the model in test data set, right? The test data set is not part of the training data set. Why? Because you want to build the data set, the model in training data set, and test it is a completely new data set which is not part of the training, right? If you test the performance only in the training data set, then it is likely to be biased, right? It will be good, but it may not work in the test data set. The whole idea of building a model is to ensure that the model performs in a new data set, right? And in order to be sure about that, you do this split, and you have this state data set for which is not part of the training data set for performance assessment. The problem with this sort of arrangement is that your test data set can be any part of the data set, need not be just this part. It can also be in this part, or it can also be this part as well, right? So how do you know actually which part of your data set is your test data set? That is where cross validation really helps, right? So cross validation is where you're assessing performance not just in one test data set, but actually in multiple test data set, in multiple samples, right? There are various ways of doing that, and we will see actually, right? So we will we will keep on changing the training and test sample from this main data set, right? Maybe one time this particular part will be training, the other part will be test, and it can change, right? This part can be the training and maybe this part will be the test, right? So if you keep on changing that, it gives you more accuracy about your performance assessment, and that's called cross validation, where you take multiple test data set to assess model performance, right? Just to get rid of the selection bias, because if you select the test data set, there may be selection bias, right? How do you know actually which part of the data set will be test data set, right? So that there could be a selection bias happening. Cross validation removes that bias actually. Okay. As I have said, so cross validation is about partitioning the data set into training and test, but in different combination, right? As I have said, if I have this data set, okay, in the first time you do performance assessment, you take this part to be training and this part to be test, okay? Second time you did, okay, maybe this part is the test, this part is the training. The third time you did, maybe this part is your test and the left and the right are the training data set, right? You keep on doing that. You can do many times, right? And that becomes cross validation, because you not just assess performance in one sort of arrangement, but in multiple arrangement. And the more number of times you do, the better the performance assessment will be, right? Imagine the accuracy rate, which is a metrics used to assess model performance of a machine learning model, is, let's say, 70% this time on the test data set B. Second time it gave 65% if you change the test data set, right? Right, but it's the same sample. It's just that the section of the data that you use for testing is different. The third time it comes out to be 68%, right? And you take the average of it, right? The performance is 68%. Imagine you had just used this particular one, right? You would have given 70%, which is not the accurate number. Actually 68% is a more accurate number compared to just 70%. So taking the average of multiple test sample is a better way of assessing model performance, and that's essential is cross validation. There are various ways to do it, but this is just one way. Okay, so what's the procedure? Okay, you partition the data into multiple into different folds. We have just seen that, right? It's essentially the same. And then you build the model in one part of the data set, test it in other. Like for example, here you build the model in A, test it in B. Similarly, you build the model here in A, right, this part, and you test it in B, and you keep on doing that, right? That's the second step. And the third is you assess the model performance. There are various metrics used to assess model performance in machine learning, whether it's accuracy rate, precision, recall, F1 score, ROC, and AUC. All of these matrices, depending on the problem at hand, you will assess the model performance, and you take the average across all the the samples that you have used, right? Remember that the samples are created from the main sample. It's not like you are taking multiple samples. The same sample used is just about how you split it, right? Cross validation gives you better generalization, right? Simply because only if you assess the model performance in all parts of the data set, only then you will have better idea about what the model performance is going to be when you use it in an unseen data, right? Because that's the whole intent of building a model, that the model should perform well in the unseen data or the new data set, right, in the future when you use it, right? And then the reduced variance, that means cross validation will ensure that model performance when you build the model is 70%, but when you use it in the production, right, for different for purposes, the model performance is reduced to 55%. The variance is high, right? There's a huge drop. That is never going to be the case. Or maybe the performance increased to 80%, right? You did not that. So that sort of variations will not happen, right? Right? You will know it beforehand, right? Imagine the performance happens to be 70%, but you did a cross validation, you check that it's not actually 70%, it is less than that, right? So you do modification, you include more features, you use better modeling techniques, you do all kinds of explorations to improve the model performance, right? But only when you know what is the actual model performance, and that's reason why better generalization is very important, right? And it reduces the variance, right? It ensures that the performance doesn't hugely deteriorates when you use the model in unseen data set. The different types of cross validations, k-fold is perhaps the most popular one, but there is also something called leave one out, very similar to k-fold. There is also something called bootstrap cross validation also. Okay, so in k-fold cross validation, actually the one actually we saw previous time is k-fold. So k represents how many times you do this iteration. So okay, it can be 5, k can be 5, or k can be 10, it can be even more, but 5-fold or 10-fold are the more popular ones. Okay, it's the same thing actually, right? You just keep on changing the split of training and testing. Okay, this part become training, this part become test. Okay, let's see, this one A, this is B. Second time you just change, this part become B, sorry, okay, this will split it. Okay, this part can become B, this part and this part will become A, right? You keep on changing that. In the A part you do the training, in the B you do the testing, right? If you do this 5 times, it becomes 5-fold cross validation. If you do it 10 times, like 10 of these splits differently, then become 10-fold cross validation, right? Right. In leave one out cross validations, it's similar to cross k-fold. It's just that instead of making it as 70-30 split, which is normally the case in training and test, right? What you do is that you build, imagine there are 100 observations, right? There are 100 observations in this case. Okay, you build the model with 99 of them. So 99 will be used for model development, that will be part of training, and that's just one, the remaining one will be used for testing purpose. and you see whether it is accurate or not, right? And how much what is the accuracy, right? And you keep changing that, right? And this 99 will always change, right? Then you take another 99 cases, right? And then another one of them, right? So each observation in this data set will be used for validation purpose, right? So there will be 100 iterations because there are 100 observations. There will be 100 iterations in this case. Each one of them, each observation will be part of the test sample, right? So this is more like a 100-fold cross validation, k-fold cross validations, but it's also known as the leave one out. Why one? Because this just one observation is used for testing purpose. Very computational intensive, but really a rigorous assessment of model performance, which is a really good thing. If you want to use this is amazing. But imagine you have, let's say, 100,000 observation, you have 100,000 observations, so there will be 100,000 iterations. That is very, 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 very computational intensive. So if you do have a big data set, go for k-fold cross validations. If you have smaller data set, maybe a couple of 100 observations, then go for leave one out cross validations, right? Cross validations can be categorized in different other types also. For example, stratified cross validation, right? Stratified cross validation will ensure that the different strata within the sample are maintained in the test in when you do the split also. For example, imagine you want to keep a right balance between the gender balance in the data set, male and female, right? That must be properly maintained when you do the sampling, because sampling is done randomly, by the way, right? So it will not, unless you specify it, it will not ensure that the the ratio is maintained. If it's in the main population, male to female ratio is 60 to 40, even in the samples this must be maintained, right? So satisfied cross validation ensure that. There can be other stratum also. For example, there can be demographic. For example, you want in a data set you have data from New York and Chicago. Ensure that that ratio of observations from New York and Chicago is maintained in all these cross validation samples. Okay, there's something also nested and not so much used actually, but you have it combines multiple rounds of cross validation. Okay, in Python actually you can use scikit-learn. It's amazing package actually. In Python you can build all kinds of machine learning model using scikit-learn, sklearn. You can also use that for performance assessment. In model selection, you can take model selection in order to do the cross validation. K-fold is more popular, but leave one out is useful when you do not have too many observations. Let's say you have 50 observations, 70 observations, 100 observations for your model building, then leave one out. LOOV, CV is a good cross validation, preferred one. What are the most important things you need to keep in mind if you're doing cross validations? Okay, the first thing is that the choice of cross validation technique, right? If you have huge data sets, right, you cannot use leave one out, for example. You have to go for the k-fold one. Right, even a 10-fold cross validation will be time taking. 5-fold will be fine, but 10-fold, well, nowadays computational intensity is, computational power is quite easily available, so that should not be a problem. But for instance, if you need a stratified cross validation, you really need to ensure that stratification is done properly, right? If you work in banking and financial sector, stratification is very, very important in banking, financial service industry. So there, ensuring that if stratification is done properly is very important, and you need to pay attention to the stratification pass. Hence, ensuring the stratification of the cross validation is done is quite important. Okay. So choice is very important, right? Choose the right cross validation. Data processing is very, very important, because before you do any building model, right, ensuring that all the data issues are addressed is very important, right? Otherwise you will be in mesh, right? Don't jump into building model and validating model unless you are sure about the quality of the data. So handling missing values, feature scaling, encoding, those basic things which we really need to do before building models. Do that. Ensure that the selection is random. If you do packages, right, if you use Python or R packages, it ensures that the selection is random. But if you do it manually, I think that then it will be a problem. Nobody does things manually anymore, so less of a problem. But if you want to reproduce the data, always use seed value, right? In cross validation, you can use seed value, and that their option is there in scikit-learn. If just put a seed value of any number, just put any number, 20 or 30, but it has to be just one number. Then you can reproduce the same sample and same results later on, right? The way you select the best model is based on the results from cross validation, right? And remember that in ML model development, the most important thing is selecting the right model. You can have hundreds of models coming out of your modeling exercise, but how to assess the best model? Now, the model that gives the best performance is normally selected, but there may be other constraint. If a model is too complex, right, it may not be selected finally, right? So those considerations should also be taken into account while selecting the best model, and not just the results from cross validations. So cross validation obviously is the most important one, but there may be other reasons to not select a good model, a good performing model, for reasons such as complexity, ease of implementation, and so on and so forth. Performance metrics, goes without saying. You really need to decide which performance metrics is best for the model. Cross validation will do the sample selection and iterations for you, but you need to select which metrics to be used. It can be accuracy, it can be precision, recall, F1 score. First of all, you need to know whether it's a classification problem, it's a regression problem, right? Depending on that, you will select the best metrics, but also the type of the problem at hand. If for instance, if it is an unbalanced data set, right, you're building a fraud model in compliance area in banking, where most of the times you will find the unbalanced data set. How do you ensure that this the metrics that you use for performance assessment is good enough, right? Pay attention to that. What is the right metrics for that? If you use wrong metrics, then no matter how good is your cross validation, it will give you wrong results, right? So very important to know about overfitting. If the cross validation result is too good, let's say accuracy rate is 97% or 99%, that is too good to be true actually. So you need to play the role of devil's advocate and challenge actually why this result is wrong. Maybe you have used, maybe it's the nature of the data set. You need to challenge yourself. So to ensure that, it is not overfit, the result is actually more generic result. Okay. Okay, interpretability is very important. Right, when you build any model, I think to be able to interpret it is very important. Remember, if you're working in finance area actually, right, in regulatory finance areas, you should be able to explain the results to the regulators, to the business people, right? If you have very complex model, complex cross validation technique, then you will not be able to explain that properly. So your choices, the choices that you have made, you should be able to explain, right? What is the value of k in k-fold? Is it 5, 10, 8, 100? What is that, right? You should be able to explain that to the regulator with justifications, right? So keep that in mind. Computational resources, well, nowadays is less of a concern, but not everybody has access to powerful servers and all that. Although nowadays it's quite cheap, you can always buy things on cloud. But if you don't have access to that, keep that in mind, right? If you are in academia with less money, less resources, make sure that you keep an eye, if you pay attention to the computational resources available to you. Okay, so these are some of the things I wanted to share with you regarding cross validation. The takeaway point here is that it is the most important thing in model building process. If you need to spend equal amount of time, if not more, on assessing model performance to what the amount of time you spend in model development, right? So that's the takeaway point, and there are many ways to do it. Choose the way that is best suitable for the given problem. Okay, thanks for watching. See you next time.